All right. Previously, we talked about like specific type of vibrating system, right? We talked about a pendulum, swinging pendulum, and a spring mass system. Now, these two systems had very similar differential equations, so we ended up solving the differential equation for one of them and used the same set of solutions or um, parameters we got for, let's say, swinging pendulum for the spring mass system. And he said in nature, if you look at their differential equation, the system response would be the same as long as we know the initial conditions. Now, what I want to do today is I want to start talking about the third element in a vibrating system, which exists in any vibrating system. Previously, we kind of ignored that parameter or element in those two vibrating systems, or the vibrating systems we were looking at up until today. And that element is damping. So any vibrating system, right, and this is a general statement, any vibrating system has three elements. Right? First one that we saw before is an element that stores potential energy. Right? The good example of that we saw was the spring. Elasticity is the same when you think about a solid material. We'll see later on when I talk about stiffness and I tell you how can we actually find the equivalent of a system using spring and mass combinations. You will see that elasticity has a very similar behavior to a spring in a vibrating system. So the first element is an element that can store potential energy. Examples of that are spring and elasticity. So let me just put these together, write them down. So I'm going to talk about damping today. I gave away the topic. Now, before that, I just want to give you the big picture of what is going on with the vibrating system. So a vibrating system, let's say a vibrating system has three elements. The first one, as I said, is an element that stores potential energy. And the example was spring or elasticity. We'll talk about elasticity a little bit later. Or in this class, maybe a week or two from now. Now, the second important element, as you can guess, well, in the spring mass system, we had a mass. In a pendulum, we had a mass. So the second element is an element that stores kinetic energy for us, right? or for the system. An element that stores kinetic energy. Example of that is obviously just mass. And if you think about it in the case of a pendulum, inertia and mass, depending on what type of system you're looking at. But both are elements that can store kinetic energy. Now, today we talk about the last element, which is damping. Right? It's a new element we are adding to the system to form a full vibrating system, I would say. So this element is an element that dissipates the energy. Dissipates the energy. And as I said, it's called damping. Now, keep in mind, right, and obviously based on the observation, we can tell that no vibrating system is going to continue vibrating or oscillating forever. If we just have a spring mass system that has a spring that can store the potential energy, right? When the spring is fully compressed or stretched, it has the maximum potential energy that it can store. And then we have an element like mass that can store kinetic energy, right? So this kinetic and potential energy keep converting to each other. Now, if these are the only two elements in a vibrating or oscillating system, obviously a vibrating system is going to oscillate forever. But no vibrating system, you can tell that from observation, no system moving is going to move forever as long as there is no forces applied to it. Right? If you give it some initial condition, like some initial velocity or displacement, and let it go, it's going to stop at some point. For some system, it might take a long time. For others, might happen in a much shorter period of time. But it's going to stop at some point, right? And that stopping happens because there is a third element in any vibrating system that dissipates the energy, and that element is damping. Now, what damping is, when I was talking about vibrations at the beginning in first class, general idea of vibration and how things work in a vibrating system, I briefly mentioned that when we have a vibrating system, in so many cases, the energy of this system is gradually converted into either heat or sound, or both of them. A very good, simple, I would say, example of it is when you are rubbing your hands together during winter time. Right? So when you do this, well, the main purpose of doing this is because you want to warm up your hands, right? This vibrating system, which is a vibration, right? It's a motion that iterates itself after a certain period of time. This oscillation, like the energy in this oscillation, dissipates in the form of heat. Right? You start feeling warmer. And you also can hear it. So both a little bit of heat and a little bit of sound comes out of this. And that's where the energy is going, the energy you're putting into this system. Right? It's a very simple example. Another example is if you plug a guitar string, right? Music. A vibrating spring is not going to vibrate forever. It stops. Why does it stop? Well, the energy is converting into sound in that vibrating system. So there is always an element that dissipates the energy. It takes the energy out of system and converts it into something else. And because this conversion happens, obviously the system or displacement of the system, if you think about a simple system like a spring mass, the displacement of the system decreases. It slowly decreases, and at some point it stops. So that's the reason why it happens, because we have an element there that takes the energy out of the system. Now, damping comes in different forms. We talk about one, the most important one today, and we talk about another one later on during the semester, which is friction. Right? We have seen friction. If you think about friction, friction is nothing but an element that takes energy out of the system, because when we have friction, it makes objects in motion stop if there is not enough force to continuously overcome that friction force. Now, let's start with the one that is the most common one, and we will deal with it very frequently in this course and later on, and I'll tell you why, which is called, that is viscous damping. Viscous damping. Now, viscous damping, right? It's first of all, it's the most commonly used, I would say, damping mechanism. We specifically use that a lot when we're modeling systems. So let me just put it here. Most commonly used damping mechanism. Now, when does that happen? Well, that's the question. Okay, well, we said this is viscous damping. The name might kind of give you some hints. Like viscosity is related to fluid, type of fluid, obviously not a solid. So when we talk about viscous damping, it happens, or it occurs when the system is within or is vibrating in a fluid medium. Right? Any fluid medium, air, gas, oil, water. For instance, that pendulum swinging is not going to swing forever. Right? There is a resistance. Right? Think about it as a drag force. Obviously, we're not modeling it in terms of drag force, but some resistance there in the fluid that stops the system from moving. It dissipates the energy, slowly decreases or reduces the amplitude of vibration or the oscillation. So let me just put it here. It happens, or it occurs when a vibrating system, let me see if I have better wording there. Okay, this is better. When the system is vibrating in a fluid medium. Example of that would be, let's say, such as I said, water, gas, oil, air, etc. Any fluid. Now, so that that resistance by the fluid pretty much prevents the system or reduces the system's motion slowly at each oscillation. So, and another reason that we start with viscous damping, because it's a very well behaved, easy to model damping mechanism for us. So in so many cases when we have a damping that when we have a system that the damping is actually not a viscous damping, we simplify that damping mechanism to a viscous damping. Later on when I talk about friction, and it's called Coulomb damping, you will see that actually it's a little more difficult to simulate or model a system with a Coulomb damping. Viscous damping is the easiest to model. Having said that, we're still going to go over some good amount of math today to be able to actually model a system with a viscous damping. So in a viscous damper, and typically the way we think about the viscous damper, right? The damper is just the element itself. Damping is the mechanism. Is we think about a piston going back and forth inside a cylinder filled with fluid. Right? That's a typical way of thinking about a viscous damper. Right? If I have a cylinder here, piston going back and forth inside the cylinder, and let's say the cylinder is filled with some fluid, some, let's say, oil. Now in this type of damping, right, remember when we were talking about the spring, we said the force is related to displacement or deflection in the spring. Now in this type of damping, the force is proportional to not displacement, but velocity of the vibrating system. So for a viscous damping, we have something like this. We say, well, Fc, if I call it the damping force, is proportional to x dot, right? Meaning that damping force is proportional to velocity of the oscillating system. Now, how do we connect these two? Right? This, we always want to go from a proportionality or some kind of relation to equality. Right? The same thing we did for a spring. We said F equals to Kx. We use the coefficient, which we called it spring coefficient, right? Spring stiffness. Now we are going to use a different coefficient. We call it C in this course. You might see it with different letters in different places, but a typical way of representing it is using C. And C is also a coefficient, is a constant which describes the damper, a viscous damper we are using. So for a viscous damper, let's say for a viscous damper, we say the force of damper, I represent that with Fc, is equal to Cx dot. Now this C is damping constant. Damping constant. Can anyone tell me what is the unit for this? For this C? Assuming that, well, knowing that F is a force and X dot is velocity.
Can you repeat the question, please, Professor?
So the question is, what is the unit for damping constant? Knowing that F is force, obviously, and X dot is velocity.
Is it kilograms per second?
Anton, I heard you said something. Can you say it again? Anton?
Well, I said something. I said kilograms per second.
Oh, okay. Kilogram per second. How did you get that? Isn't the unit for force Newton? I mean, I know it's not wrong, but if you go from this, technically this is Newton, right? And this is meter per second. So C would be Newton over meter per second, which gives us Newton second per meter, right?
That is correct, Professor, but Newton's is kilograms times meters over second squared.
Yes, the kilogram per second is correct too, but I was just curious, how did you get that? I guess you went one step further, but that's correct too. That's also another unit you can use. But typically we use Newton second per meter. All right. It's just one step further, you simplify that, you get there. But I'm happy that you went that far. Just typically we use Newton second per meter, as opposed to Newton per meter for, not as opposed to, similar to Newton per meter for spring. Now that we know damping, let's take a look at the most simplest system with a damper, viscous damper. Right? That's what we want to do. We introduce the damper. Now let's see what happens if we introduce this element to the system. Right? So let's say I'll call it for a spring. Now we have a damper, right? So I'll call it a spring mass damper system. Now we represent, if I have a mass there, that's what we always do. We solve the equation, or we figure out how does the motion happen for a simplest form of the system, and then we start from there. We use that. So we represent damper with some element like this, viscous damper. If it's kind of symbolic version of that cylinder, piston cylinder, and we use C to represent that damper. So now I have a system with a spring and a damper. I'll do what I did for a spring mass system. I start with, well, now let's study the motion of this and see where does that take us. So if I look at the free body diagram for this, let me draw it here. And let's say this is, let me use this different color. Let's say this is the equilibrium point. I'm giving some initial velocity displacement to one direction, to this mass. So if I draw the free body diagram, well, that would be some reaction force. We have the weight there. It's going to the right. Damping behaves very similar to a spring in terms of the direction of the force. So every time my system deviates from the equilibrium point, you remember before I said spring tries to push the system back to where it was, to its equilibrium point. Or you can think about it this way, actually. A spring, what happens when you're in equilibrium point, right? A spring tries to go back to its initial length, and damper tries to push the system back to its equilibrium point. The easiest way to think about it is that both of them are trying to push the system back to its initial, to its equilibrium point. So in this case, if I'm pulling the system to the right, the spring is trying to take it back to where it was to left with force kx, and damper is also trying to take it back to where it was, to equilibrium point. But the force in damper is cx dot. Right? Now this is my free body diagram. Kinetic diagram, or the inertial forces, I have only one thing, mx double dot, or ma, you want to call that. But the acceleration is pretty much the second derivative of displacement with respect to time. So if I write the equation of motion, or I use the Newton's second law, summation of forces equal to ma, and we're talking about the x direction, I don't care that much about y direction. There is no motion, n is equal to w. This gives me what? It gives me minus kx minus cx dot is equal to mx double dot. And from there, you get mx double dot plus cx dot plus kx is equal to 0. This is the differential equation, or the equation of motion for a system with a spring and a viscous damper. It's the general form of the equation. Now, this form of the equation, again, this is also a second order differential equation. As you can see, we have x double dot. Now, one thing has changed compared to the equation we had from before. If you remember, for a spring mass system, what did we have? We had, for a spring mass system, I had mx double dot plus kx is equal to 0, right? From before. But now it's changed. So I cannot use what I have from before. Before I solved that differential equation, that second order differential equation. Or I solved it for a pendulum, and I found this is very similar to pendulum, so I use the same set of solutions. But now it's a new differential equation. This is a second order differential equation. It's homogeneous, it's linear, but it's different. We have x dot there now because of the damper. So we have to solve this again. Now let's see how can we solve it. So we have a second order differential equation we're trying to solve. Depending on how much you remember from your course differential equation, let's say for mx double dot plus cx dot plus kx is equal to 0. All right, it's a second order linear differential equation. I had to put it's homogeneous. The right side is 0. Do you remember how were we How were we solving? How could we solve this from that course? What was the general procedure to solve a differential linear differential equation, second order homogeneous one, or could go also for non-homogeneous? As I said, vibrations is applied dynamics. In dynamics, we would have just stopped here. We say, well, this is the equation, that's it. Now, vibrations, we have to actually solve this and find the system response, or find the way the system behaves and it moves. We want to find x as a function of time, or velocity or acceleration as a function of time. So I'm hoping that what I say is going to refresh your memory from differential equation. I'm going to talk about characteristic equation. Remember, when we were solving this, we were using characteristic equation. We were finding characteristic equation for a second order differential equation. And depending on the roots of that characteristic equation, we could guess, or we could come up with the general form of the solution for a differential equation. So the way it works is that, let's say I guess I'm saying xt is equal e to lambda t. Lambda is a constant. Different books use different constant. It's just a constant. So x dot t becomes lambda e to lambda t, take derivative with respect to time, and x double dot t becomes lambda squared e lambda t, these three. And I'm going to plug these into the differential equation because I want to convert my differential equation into an algebraic equation and find the roots of that equation. So this becomes m lambda squared plus c lambda plus k times e to lambda t is equal to 0, if I didn't make any mistake. Now, well, I have two elements multiplied and they become 0. We're not interested in when e to lambda t becomes 0. We're interested in when this becomes 0. So I'll say, well, from there, m lambda squared plus c lambda plus k is equal to 0. And this is just an equation, typical equation we can solve. It's an algebraic equation. Think about this as ax squared plus bx plus c. Right? We can find the roots for this. So the root for that, roots for that would be lambda. I'll just put both of them together. Right? It gives us two roots. Minus c plus minus square root of c squared minus 4mk divided by 2m. Remember from solving a typical equation when we had ax squared plus bx plus c, we said we had minus b plus minus the square root of b squared minus 4ac divided by 2a. So this is just the same equation, the same form of equation we had, and we get two roots. Right? This plus minus plus gives us one root, minus gives us, this one gives us two roots. And these two roots, or the number of roots we get, actually I have to say, because we don't get always two roots, tells us what is the general form of the solution for the differential equation that we got this characteristic equation for. This is the characteristic equation. This is the equation. I'm going to go through a good amount of math today, so I want you to be present mentally and follow. Okay, so let me see. I want to make sure that I follow. I tell you everything. Okay. Now, I can actually write this in this form: minus c over 2m plus minus 1 over 2m square root of c squared minus 4mk. It's pretty much the same thing I divided by 2m. Divided each component on numerator by 2m. Now I'm going to define two things. Right? The same way I defined natural frequency and time period when I was solving a differential equation for a spring mass system, I'm going to define two things. Actually, three things. I'm going to define two things first, and later on we'll see I'm going to define another thing. These are new concepts. Right? This is the theory of vibration we're studying. So we're introducing new concepts to be able to actually speak the same language, right? To speak the language of vibrations. So I define, let's do it this way, two things. First, I define the concept of critical damping, and later on you'll see why it's defined this way. It's called C, typically they represent that with CCR, C critical. And I define that as 2m omega n. Omega n is the natural frequency of the system, square root of k over m. So if you replace that, you will get 2 square root of mk. Either of these. This is critical damping. And knowing that, I use that to define something else also. Damping ratio. What is damping ratio? Well, the ratio between the damping in the system, C, the value of damping constant or damping coefficient, we call it damping coefficient sometimes in the system, over critical damping. So I represent that with zeta, like Greek letter zeta. It's C over CR. You can replace what you had from critical damping to M omega n, or C over 2 square root of mk. So I introduced these two concepts. Keep them in mind: critical damping and damping ratio. Now I use these two concepts to rewrite the equation I got for the roots of that characteristic equation, this equation. I'm going to rewrite that. If you plug these in and move things around, you actually get something along this line: minus zeta omega n plus minus omega n square root of 1 minus zeta squared. If we put it correctly. The other way around, zeta squared minus 1. You should be able to get this plugging in the values, these two definitions. Now, these are the roots, right? The equation for the roots. I'm just going to add it here. Equation for the roots of characteristic equation. Right? Gives us two roots, lambda 1 and lambda 2. Now again, depending on how much you remember from differential equation, depending on what those roots are, right? Actually, I'm going to correct myself. It doesn't give you two roots all the time. Well, technically it does. Okay, let's go with that. Depending on what those roots are, you will go with the given or a suggested form of the solution for your differential equation. Now, how do they change? So in this case, I'm going to have in this situation, I'm going to have three cases. If you look at this, this part of the equation, like the square root part, this part. Now, this zeta squared minus 1 can decide how many roots we are going to get. If zeta is equal to 1, what happens? What do we get out of this if zeta is equal to 1?
0.
This part becomes 0. So pretty much lambda 1 and 2 is equal to minus zeta omega n. Right? So two roots, we're going to have two similar roots. Or we get same roots, or we get a repetitive root. Because it just becomes minus zeta omega n. Now, if zeta is greater than 1, this value under this square root is positive always. Think about it. Zeta squared minus 1. If zeta is greater than 1, that value is always positive. So we get two real valued number, some numbers. One for lambda 1, if you go with plus, and if you go with minus, here, I'm talking about this. If we go with minus, we get another root. So we get two roots, real values. Now, if zeta squared is less than 1, so the value under this square root becomes less than 1, becomes negative. And the square root of a negative number, well, you know that from before, it's a complex value. It's not a real value. So we get two roots this time. Both of them are complex numbers. So depending on what the value of zeta is, we're going to have three different cases. And for each case, the suggested form of the solution for that differential equation here changes. Remember, we are looking for a general form of solution. In a spring mass system, I told you, well, it's mx double dot plus kx is equal to 0. I'll suggest a sine omega nt plus phi, like a sine omega nt plus phi, and let's find the coefficients from initial conditions. Now, this case, the suggested form changes depending on what the roots are, or more specifically, what the value of zeta is. So we're going to take it from there. I'm going to say the first case is when zeta squared is, or zeta squared minus 1 is smaller than 0. In this is a situation when this the value under the square root becomes negative, and we're going to get two complex roots. Now, if this happens, well, you can infer from that if zeta squared minus 1 is minus 1 is smaller than 0, you will get zeta squared smaller than 1. We don't care about the negative part. So zeta becomes smaller than 1. Technically, zeta becomes smaller than 1 and greater than minus 1. But we don't care about the negative part. Let's just stick to the positive part. So what was zeta? Zeta was C over C critical, right? I defined it here as a damping ratio. So I'm going to use that to say, well, if zeta is C over C critical, this means C is smaller than C critical for this system. This is important, right? Because this...
Would that be underdampened?
Yes. So we call this, because C is smaller than C critical. Remember, C critical is just a function of mass and stiffness, right? Sorry. Let's go back to the previous slide so I talk on that. It's C critical is 2m omega n, or 2 square root of mk. As long as you know the stiffness and mass, you get the critical damping value. So see, if the damping for the system is smaller than critical damping, we are in this case, case 1. And that's why we call this underdamped. Right? Underdamped system. Sometimes they just put them together. Underdamped system. Now, if this is the case, the suggested solution for the differential equation that we have is xt. I'll just give it to you. And that's pretty much how it works even in differential equation. You actually don't get it. You just, if you remember, as I said before, we actually don't solve differential equations. We just have a set of suggested solutions for different form of differential equations, and we just have to figure out what form we're dealing with and use that suggested solution, general form of the solution, and find the coefficients in that solution. That was a general procedure in differential equation. Do the same story here. So I'll tell you that the suggested solution, right, for this case, actually, let me define another thing before we go further. So here I'm going to define another thing. I remember I told you I'm going to define 3 things. 2 things I already defined: damping ratio and critical damping. Now I'm going to define the concept of damped natural frequency. So damped natural frequency, right? We already had natural frequency before. Damped natural frequency, which is specifically for systems that are underdamped, or when C is smaller than C critical, we show that with omega d is omega n square root of 1 minus zeta squared. This is another important concept you're going to hear me saying over and over. And the unit for this is still radian per second, right? Because damping ratio has no unit. 2 dampings are divided by each other. The one is divided by the other, so the units cancel out. So omega d is just a damped natural frequency with the same unit as natural frequency, but it's for a system, for an underdamped system. So I can use this and rewrite this equation for roots, right here, this one, lambda 1 and 2. Here I have zeta squared minus 1. So I have to move things around a little bit to replace this omega n square root of zeta squared minus 1 with omega d. Here is what I'm going to do that. I will say lambda 1 and 2 is minus zeta omega n plus minus omega n times square root of zeta squared minus 1 times the square root of minus 1. I took 1 minus 1 or factored out 1 minus 1 from that square. So now it's zeta squared minus 1, and took it out is square root of minus 1. Square root of 1 minus 1 is I, right? Complex numbers, if you remember when we were dealing with complex numbers. Square root of minus 1 is defined as I. So I can rewrite this as minus zeta omega n plus minus, right, omega n square root of, I had to actually switch that, which I didn't. Right? It was already zeta squared minus 1 here, so I have to switch it 1 minus zeta squared. Sorry for the confusion, because when we take out 1 minus 1, this becomes negative, 1 becomes positive. This becomes 1 minus zeta squared I. Right? And here we have, this is now omega d. Now, what is the general form of the solution? So now I can give you the suggested solution. So from differential equation, suggested solution for this, for the differential equation we're dealing with at the beginning, mx double dot plus cx dot plus kx, is xt a e to minus zeta omega nt sine omega dt plus phi. Right? Don't ask me how did I come up with this. Take a look at your differential equation notes. Hopefully that refreshes some of your a little bit of your refreshes your memories. But once we have two roots, that complex roots, two complex conjugate roots, as we call it, right? Something plus minus complex value. This is the suggested solution. Now, our job is to find the coefficients in this solution. We don't know what A is, and we don't know what phi is. Do you remember we did the same thing with the spring mass system? We're going to do the same thing here. Everything else we know. Omega n we know. Omega d, as long as we know the damping, we know the system characteristics, mass, stiffness, and damper, we can find omega d as well. So we need to find A and phi. Let's see how do we find those. I'm going to do the same thing I was doing for spring mass system. Given an initial condition, a set of initial conditions, let's go with whatever is happening at the beginning of the motion. So initial conditions, x at t equals to 0, displacement, wherever the system is at the beginning of the motion, I'm going to call it x naught, would be, well, plug in t equals to 0 to the suggested solution. Right? This is a general solution, so it has to be valid for every moment during the motion. This moment I'm considering is the moment that the motion starts. So at t equals to 0, well, we get rid of this one. This becomes A sine pretty much phi. That's pretty much it. Now, for initial velocity at t equals to 0, I'm going to call that x naught dot. Take a derivative of this first. Actually, this is a long derivative, so let me do it here. Now, d dt, I'm going to take a derivative with respect to x, the suggested solution, xt. Now, we have two components multiplied by each other, both functions of t. I'm going to find the derivative with respect to time of the first one, multiply that with the second one, and then multiply the first one by the second one, whatever is its derivative with respect to time. So I'll say A, well, let's take derivative with respect to first one. This is the first element. It has t, and this is the second element. Both of them are multiplied. So I'll have to do the multiplication, take the derivative with respect to this multiplication of two functions of t. So we take the derivative with respect to first one. This becomes minus A. Keep in mind, we're taking derivative with respect to time, so everything else is a constant for us, as long as it's not a function of time. Zeta omega n, right, So I'll take derivative e to whatever it is. I'll take this comes to whatever down behind the a, so it becomes minus zeta omega n a, right? And let me just make sure that I'm doing the right process. I don't want to go in the middle and somewhere things get lost. Yeah, okay, that's good. So I take derivative with respect to the first one and multiply with whatever we have as the second function. And now I do that for the second part. So the derivative with respect to time, right, is it's going to be plus. We'll see how it goes. Now I have to take derivative with respect to time for sine omega dt plus phi. All right. If I do that, just want to double check. That's what I did. Right. Yes. So sine omega dt plus phi, right? Omega d comes out. Right? This becomes omega d. I'll write the first term here. That doesn't change. Omega n t. Sine becomes cosine, and whatever we have inside that parentheses. So this is x dot t. Now let's put t equals to 0 in this. The reason I did that because I wanted to find what is the form of this general solution at the beginning of the motion, right? Velocity is equal to 0. So if I put t equals to 0, well, this sign is gone. This gives me minus a zeta omega n sine phi, right? Just want to make sure that I got the same thing. Yeah, okay, so good. Plus, well, I put t equals to 0 here. This element e to minus zeta omega n t is gone. Cosine omega dt becomes cosine phi. So it becomes omega d a cosine phi. Right? As I said, I'm going to go through a little good amount of math today. So the idea was that I want to use these initial conditions to find these coefficients a and phi that I'm looking for. Let's see how can we do that. Right here now I have two equations, two unknowns. Right? These equations, I don't know what is the value of a, what is the value of phi. As long as I know system characteristics, we can find other things. Now, first step I'll do a couple of tricks to get what I want. Right? Instead of solving this because it's a nonlinear set of equations. I'll divide the bottom one by the top one. So I divide this by the top one. Pretty much what I'm trying to say is that I'm trying to find x naught dot over x naught. Right. Let's see what happens if I do that. Well, the first element divided by a sine phi, well, a sine phi is gone, so what is left of this is going to be minus zeta omega n. So this becomes minus zeta omega n. And the first element is divided by a sine phi. Now the second element divided by a sine phi, well, a, we canceled by a. We're going to get omega d cosine over sine, right, plus omega d cosine over sine, which I use cot for that, like the 1 over tangent, right, cotangent. So now you see I got rid of a by doing this. So I'll be able to find phi from here. If I move things around, let me do it step by step. So it would be omega d cot phi is equal to x naught dot over x naught plus zeta omega n, which you can move you can write it this way, right? X naught dot zeta omega n over x naught plus zeta omega n x naught, I guess. Multiply that. Oh, why did I do it the other way? I don't know why I do it the opposite way. I guess I have in mind that what is happening next. So this becomes the fraction. This becomes x naught zeta omega n. Then this becomes x naught dot plus zeta omega n x naught. Hopefully now it's correct. Did I do it correctly? Actually, hopefully I did. For some reason I'm stuck there. I tell you to have a present mind, and I don't have it myself. No, this becomes pretty much just x naught. It's very quiet there. Tell me what did I do wrong, guys? Multiply that plus this. Now we're good. I believe so. So this becomes cot phi is equal to, I'll take omega d down there, x naught dot plus zeta omega n x naught divided by x naught. I can't write it better, x naught. X naught omega d. Now I want to find phi. So this is cotangent. It's 1 over tangent. So if I flip everything, tangent would be x naught omega d over x naught dot plus zeta omega n x naught. So you can find phi here. Tan inverse x naught omega d over x naught dot plus zeta omega n x naught. So after doing all of this, here we are. This is the equation for phase. So as long as I know what system's initial velocity is, what system's initial displacement is, and I know the damped natural frequency and natural frequency, which I can calculate knowing system characteristics, I can find phi. The next step is to find A. I guess I can just stop here and find A next class. So I'll give you about 5 minutes before the quiz, because it takes a little bit time. Let me stop. Any question, guys? I know your mind probably is a little involved with the quiz.